Okay, I think we can start. Good morning, everyone. Welcome to this first session of the Indian Time Band. It's titled Software Security 1. We have four speakers. The first speaker is presenting a journal first paper, and the paper is titled Deep Learning Based Vulnerability Detection. Are we there yet? And the presenter is Shaikat Chakraborty from Columbia University.
Shall I start?
Yeah.
Okay, let's start sharing with my screen. So hi everyone, my name is Shaikat Chakraborty, and today I'm going to present our paper, Deep Learning Based Vulnerability Detections, Are We There Yet? In this paper, we investigated current deep learning based vulnerability detection techniques, their limitations in detecting real world vulnerabilities. The goal of this paper is to shed light on the insufficiencies of current techniques. Let us look at what vulnerability is. Source code vulnerability is the flaw in the code that can create potential risk compromising the security of the software. For instance, this is a vulnerable code because of this sprintf functions here can write to a buffer of unknown length. It can overwrite some important safety critical information in the memory. A very well studied approach for vulnerability detection is static analysis based vulnerability detection, where the analyzer takes in the code any other syntactic, semantic, and functional metadata available to the code and predicts whether the code is vulnerable or not. A deep learning based vulnerability detections implements such an analyzer using a deep neural network. Such a network is trained on large collection of data and formulates the problem as a code classification problem. A typical pipeline on deep learning-based vulnerability detection involves creating and preprocessing data from different databases, designing and building suitable models, training the model, and finally evaluating the model on vulnerability detection datasets. With that speed, we evaluated existing vulnerability detection techniques in two real-world vulnerability datasets. Among these two datasets, we collected this reveal data from issue trackers of Chromium and Debian projects. And here is the results of these techniques into these two datasets. And evidently, the performance of these approaches in these two datasets are far from being effectively and reliably used in development pipeline. We have identified two major sources of problem to explain this result. And in the rest of the talk, we are going to discuss these problems. First, let us discuss the issues with existing datasets. A lot of the existing techniques are trained on synthetic and semi-synthetic vulnerability code where the vulnerability is often isolated. For instance, this code is a buffer overflow vulnerability. Here, the vulnerable code is isolated. Real-world vulnerabilities are much more complex than this. For instance, in this code, the vulnerable pattern is much more obscure and complex. Thus, we conjecture that the training data should be real-world source code. That is, any deep learning model should be trained on source code example that resembles real-world source code. With that spirit, we designed a prototype for data collections, and we collected a large corpus of vulnerable and non-vulnerable code from Chromium and Debian. Now let us move on to the next part where we investigated the problem with existing model and identify the issue with existing model. As we have seen earlier, this code is a vulnerable code, and we trained Russell et al.'s CNN-based model to detect the vulnerability here, and the model indeed predicted this code as a vulnerable. However, when we poked the model a little bit and added some explainability to the model, we see that the model thinks this red part of the code is responsible for this code being vulnerable. And evidently, we can see that this part of the code has nothing to do with the vulnerabilities. We conjecture then even when the model is doing the right thing, the model is doing it for a wrong reason, which proves that the model is picking up wrong signals from the data and becomes very brittle. In fact, if we look closely, we see that a lot of the existing models are sequence-based models, and we hypothesize that a sequence-based model lacks the capacity to analyze different structural informations in the code, which has historically played a very important role in detecting vulnerability. With all these lessons learned, we designed Reveal, a graph-based tool to detect vulnerability in real-world software projects. Given the training data, we extract the code property graph, then we use a graph neural network to generate the graph-level features for that graph, and then we do resampling to reduce the imbalance bias and do representation learning to train our tool Reveal. And when we analyze the performance of Reveal in our datasets, as we can see, Reveal outperforms all the existing baselines. So to summarize, the summary of the paper is that deep learning based vulnerability detections are far from being perfect and far from being effective. More research are needed for deep learning based vulnerability detection to be effectively used in real world vulnerability detections. And thanks for listening to my talk, and I will be happy to answer any question.
Thank you, Shaikat. Sorry. We will first have the talks, and then we will open the, we will have discussion. So I guess I will invite the next speaker to thank you very much to share the screen. The next speaker is Zi Zhang from Peking University, and will introduce ReMOS, reducing defect inheritance in transfer learning via relevant model slicing.
Okay, thanks. And let me share my screen. Hello. Now let me introduce. Okay, let me introduce our paper, ReMOS, reducing defect inheritance in transfer learning via relevant model slicing. We know software reuse is a common practice for software engineers. For example, importing third-party libraries is widely used by the developers. DNN model is now a new generation of software, and the model reuse is also called transfer learning. In transfer learning, a company collects a large-scale dataset and trains a general DNN model and updates this model to the internet. An individual developer can download this model, prepares a small-scale dataset, and fine-tunes the model. Then the final model is a specialized DNN that only performs certain tasks. In transfer learning, the general DNN is often called the teacher model, and the specialized DNN is the student model. And the student model trained via transfer learning has high performance, fast conversion speed, and needs less training data. However, despite the great convenience of the software reuse, the vulnerability propagation is one of the most concerning issues. One famous example is the heartbleed bug in the OpenSSL library. And due to the widely usage of the OpenSSL, the bug may threat all SSL-based communication applications. So similar to the traditional software reuse, transfer learning may also inherit defects. The teacher may inevitably contain some errors, thus the fine-tuned student model may inherit similar defects. So we summarize two major defects: causative defects, such as the DNN backdoor, and exploratory defects, such as the adversarial vulnerabilities. For the adversarial vulnerabilities, the attacker first downloads the teacher model and analyzes this model to find some bugs in the teacher DNN. These bugs may be inherited by the student and be used to attack the student applications. For the backdoor, the attacker can intentionally poison the training data, and then the training DNN is some special backdoor. After the developer fine-tunes the student model, the backdoor remains and threats the downstream applications. So we surveyed prior literatures and summarized several defects. The experimental results show that the defect inheritance rate ranges from 52% to 97%, meaning that this problem is a real threat in DNN model reuse. We here illustrate the defender score with this Venn diagram. For conventional transfer learning, the teacher and the student share much knowledge, but we aim to compress the shared knowledge so that it contains mostly the student-related knowledge and excludes the unrelated knowledge. To reduce the defect inheritance problem, we propose to use the relevant model slicing, which is also called ReMOS. ReMOS is motivated from relevant slicing, which computes the statements that have the potential to influence the target variable. This figure illustrates an example. The code snippet contains a potential defect. If the input B is 0 and divided by 0, error may occur at line 8. Directly reviewing this code snippet will inherit this defect. But if we know the input domain is A less than 1, we can select the criteria and slice the relevant parts. The defective statement is excluded by the relevant slice. Similar to the relevant slicing for programs, the relevant slicing for DN aims to extract the weight subset that is more relevant to the student dataset. As the teacher contains general knowledge, it is possible to select different weight subset for different student tasks, thus minimizing the possible inheritable knowledge. RAMOS consists of 4 stages. Coverage frequency profiling uses the student dataset to compute the weight relevance to the student task. Ordinal score computation computes a weight score based on the static teacher's information and the dynamic student's information. And the third step identifies the relevant slices, and the last step fine-tunes the slice. Our evaluation implemented various defects. For example, inspired from the prior work on the DN testing, we evaluated RAMOS on neural coverage guided adversarial vulnerabilities. The result shows that the RAMOS eliminates averagely 63 inherited defects. In the end, to summarize, we found that the popular DN model reuse faces defect inheritance problem like traditional software reuse. We identified 2 possible inheritable defects, adversarial vulnerabilities and DN backdoor. And the defect inheritance problem can be mitigated by reusing only the relevant slice instead of the whole model. We propose RAMOS, a relevant slicing technique that can mitigate over 60% of the CV defects and 40% of the NLP inherited defects. That's all. Thank you.
Thank you very much, Zizi. So we can now ask the third speaker to come to stage. The speaker is Larissa Brass from University of Zurich, and their talk and their paper is titled Less is More, Supporting Developers in Vulnerability Detection During Code Review. This is a paper accepted at the technical track.
Sorry. Can you see it?
Yes.
Okay, thank you. So I'm Larissa, and I'll present our paper Less is More, Supporting Developers in Vulnerability Detection During Code Review. To avoid vulnerabilities, organizations, they are shifting security to early stages of the software development, such as during code review. However, reviewing source from a security perspective has proven to be a difficult task. Previous research has shown that developers, they often miss popular and even easy to catch vulnerabilities during code review. So developers' mental attitude may be the reason why vulnerabilities go undetected during the reviews. For example, a developer may not consider security as their responsibility. A potential solution is giving explicit instructions regarding security during the reviews. And in addition to that, the use of checklists to support developers in code inspections has been studied with positive results. Yet, the effectiveness of the checklist in contemporary practice and to support vulnerability detection has not been established yet. To investigate these 2 hypotheses, we ran an online experiment with 150 participants who reviewed some code with 2 vulnerabilities in that. We split the participants in 4 groups: the baseline, where we asked developers to perform a code review task without giving any special instructions, and 3 treatments. And the first one, we asked the developers to perform the review in a security perspective, like we specifically asked them to think about security. The second one also received instructions plus a checklist that we created based on the OWASP code review guideline. And the last one that also received instructions and the checklist, however, a tailored version of the checklist. The code change contained 2 vulnerabilities that were chosen based on their prevalence, recognition, and discoverability. And discoverability regarding the checklist that we used. And 2 security experts review the code change and confirm the vulnerabilities are relevant. These are the results of the review in terms of vulnerability finding. 92 participants found at least one of the vulnerabilities. 37% of the participants found the first one, while 53% found the last one. Our results show that participants assigned to any of the treatments are 8 times more likely to find a vulnerability than those assigned to the baseline. Our analysis confirmed that having instructions to focus on security is significant to detecting vulnerabilities during code reviews. But there is still one question that is open. What is the effect of providing a security checklist in addition to just asking developers to focus on security? So to test these, we removed the participants from the baseline group and set the treatment that just received the instructions as the reference level for our logistic regression models. Our results show that the presence of a security checklist does not affect the detection of the software vulnerabilities during code reviews, compared to only asking developers to look for the security issues. Our results suggest that developers' mental attitude play an important role in the detection of software vulnerabilities during code review. The analysis results strengthen the questions on the effectiveness of the current development process, including coding and reviewing activities. Organizations may consider incorporating secure code reviews into their development process to create a approach, for example. However, further studies still need to be designed and carried out to determine how to better support and design secure code review and to evaluate its effectiveness. Surprisingly, we also found that security checklists do not facilitate the detection of software vulnerabilities compared to just instructing the developers to focus on security issues during the review. A possible problem of the checklist is that they are often too general and not sufficiently tailored to the particular development environment. However, our results indicate that a security checklist is strictly tailored to the code change does not increase the vulnerability detection in code reviews. Our findings raise questions on whether the problem is not the security checklist, but how developers perceive them. In fact, a few developers even reported to have read the checklist only after reviewing the code, or to just ignore it and not consider it at all. Further studies can be carried out to investigate how to effectively address security instructions during secure code review and to integrate security checklists in tools and processes to support the review. To sum up, our results provide evidence supporting the mental attitude hypothesis, and they call for further studies on security checklist effectiveness and design. Thank you for your attention.
Thank you very much, Larissa. So we are now giving the stage to the fourth talk. The fourth talk is titled APER, Evolution-Aware Runtime Permission Misuse Detection for Android Apps. The speaker is Xinan Wang, and from Southern University of Science and Technology, and this paper was accepted at technical track.
Okay, can you see my screen?
Yes, we can see your screen, but you need to put presenter mode. Yeah, exactly, perfect.
Yeah, so now it's in presenter mode. Okay, then I'll start my talk. Okay. Hello everyone, this is Sunan, and this work is about the Android permission misuse issues detections. Sorry. So we all know privacy and security is essential for mobile software users, and that's why Android has a permission model to protect user data and system resources. Before Android 6.0, in order to install an app, you remember that the user must accept all its required permissions, and moreover, all permissions cannot be revoked after the app is installed. And so this static model is not secure enough. So since the version 6.0, apps should use the runtime permission model instead. This new model allows the apps under this model to request permissions at runtime instead of the install time, and it also allows user to revoke the granted permissions. And so the change of this permission model can improve privacy, but it needs more programming effort to maintain. So if an app wants to obtain some sensitive data like location or contacts, it should call some Android APIs that needs permissions. we call them dangerous APIs. And the Android's official documentation will write an API needs which permissions lie in this way request. Similar to this example, it says this API needs either of these two permissions. And so an app needs a series of operations to maintain the permissions. So we also call them the runtime permission management, these steps. There are 5 steps in total, and there's an important step is to check whether a permission has been granted by the user by invoking the check API. An example is this check self permission. This API is provided by the Android SDK. And without this step, a dangerous API can be called without granting the corresponding permissions. And so that's caused some abnormal behavior. Under the runtime permission model, developers should write more code to maintain the permission. And as we all know, more code means much easier to cause bugs. So we call these bugs as ARP issues. In our work, we classify 2 types of such ARP issues. They are type 1, which is related to missing permission checks, and type 2 is related to compatibility issues. And how can we detect these bugs accurately? We figure out there are 2 major challenges. The first one is that we should properly model the asynchronous permission management and usages. And if you have background on Android development, you might know Android programs are event-driven, so there are many possible program entry points that are called asynchronously. And such programming style allows developers to write their permission management code and usage code far apart, and the user can revoke permission. And between these asynchronous events, the user may revoke the permissions. And so another challenge is about the permission evolution. For example, during the evolution of Android, the dangerous APIs may be added or removed from the framework, and also the required permission may be changed. And also the permission mechanism itself is also evolving. So an accurate detector should take this problem into account. Let's move to our tool design. Our tool Aper is a purely static detector. We define the following 4 types of permission management relation in the master call graph. So we take the intra-procedural case as an example, in which the permission checked is the blue circle and the dangerous API, the red circle, they are called from the same method. And here's the constraint such that the permission check must be happen before the check should be called before the dangerous API, or otherwise the dangerous API can be called without check and thus cause when the permission is missing, the API call will fail and result in the crash to the app. And so such app can be analyzed by a domination relation from the static analysis. Aper will analyze such calling relations. We will analyze the domination relations between these 2 types, API and between the methods. And so for check, the API must dominate the check API must dominate the dangerous call. On the other hand, the dangerous API should not be invoked before a check API, or they should not be called in parallel. And Aper deals with asynchronous events in the following way. For inter-callback management, we use the lifecycle model to describe their calling order. And under this lifecycle model, breaking the temporal order can result in type 1 bugs. And to analyze, and this is how we analyze the intercomponent management. We should build some method call graph structure, and that's also huge work. And so we finally also analyze the runtime version checks so we can detect compatibility issues. So to evaluate Aper, we run it on a set of open source apps, and the apps are collected from AppDroid by some filtering condition, and totally we analyzed 214 apps, and we found several bugs. And this is some example like this. If we enter the app and do some operations, and then if we revoke the permission and back to the app, it will crash. Also, this is a type 1 bug that is caused by permission revoking. And this is another bug which caused the same operation on two different devices and produce different inconsistent results. Yeah, so this is a type 1 bug, type 2 bugs, and this video can be showed on our website. And that's all my presentation. Okay.
Thank you very much. Let's thank to all the speakers, and I'm going to now open the stage for questions. Regarding the questions, I guess we can operate in different ways. Like you can type your question on the chat list, or you can unmute yourself, whatever you prefer. But of course, when typing your question, please specify the name, the number of the paper, or the paper to which the question is addressed, because we have 4 papers in the same session. So I'll start the conversation. So I have a question for the first author of the paper. No, so the first paper in the session, and I was wondering whether the features that you have collected training a machine learning model have a way to include information about the context where each instruction is present. Because you can have a vulnerability in a specific point in your code. However, the fact that that instruction represents the vulnerability depends on the context around that instruction. And for context, I mean the instruction immediately before and after the place, the location where a vulnerability is present. And I was wondering if you have any way to represent the context of the instruction where a vulnerability is present in your approach.
Right, that's a very good question. So the way we modeled it is we actually extracted a code property graph from a source code. So the code property graph is a graph that encodes all possible structural and semantic relationship between components. For example, say control flow, data flow, control dependency, def use chain, and as well as the abstract syntax tree. So essentially our hypothesis is that if we throw everything to the model and let the model decide what, say, now I give you a collection of vulnerable codes, and these are the graph corresponding to the vulnerable codes, and a collection of non-vulnerable code, these are the graph corresponding to non-vulnerable code. Ideally, the model should learn what is responsible for what is actually responsible for vulnerability. However, when we actually dug deep, when investigated more, we have found that the model is not, as of now, as of today, the model is not capable enough to do that by itself. And that is one of the biggest point in our study, that the model are all these models are very good and everything, but we should be cautious. We should be cautious while adapting a model in our real world, say, development pipeline, in our real ID.
So maybe can't you think about forcing the model to considering only the neighboring instruction that are linked to the one that contains vulnerability, because there is a dependency, for example, data dependency or control flow dependency. Maybe this could be a way to go to address this problem.
Yes, that is actually a good way to go. In fact, not this paper, in a later project we have been working on slightly modifying a code function and kind of investigate the effect of that modifications to reason about what is actually the modification is doing. In that way, we are kind of not directly, rather indirectly understanding what portion of the code is doing what. and thus indirectly implicitly understand what is actually reason for vulnerability, what is not non-vulnerability.
Thank you. Thank you. Actually, we have another question for you, Shaikat, from Kushal Ramkumar. The question is, are any coding guidelines recommended for the model to work? So should the source code be written in a specific way in order for your machine learning approach to work?
In our paper, we did not investigate on the coding practices, but that is a very good point. That should be investigated. But that was kind of out of the scope of our paper.
Thank you. Thank you. We have a question for Ziti, the paper 2. So will vulnerabilities present in the selected slices be inherited?
Sorry, can you repeat that question?
So basically, the question is from Kushal Ramkumar, and the question is related to the presence of vulnerabilities in the slices of the model that are selected. And the question is whether the vulnerabilities that are present in the selected slices are still inherited in your.
Do you mean the vulnerabilities in the slice? Maybe introduce some. Does the slice introduce some new vulnerabilities?
The question doesn't specify. It just asks if the vulnerabilities present that are present in the slice that you select are inherited in the student model.
I think there are indeed there are some vulnerabilities in the student model, but our goal is to minimize the common knowledge, the common vulnerabilities between the teacher and the student, because the teacher is available in the internet and anyone can download analyze the teacher. So we don't want to. Our goal is not to eliminate all the vulnerabilities in the slice in the student model, but to minimize the shared knowledge so that the student model is not that easily to be attacked. Because in the student model is too similar, has many similar vulnerabilities between the teacher. The attack surface is too big, and the attacker can use the similarity to attack the student. So our study is try to eliminate some unrelated knowledge and some potential vulnerabilities in the student model.
Okay, thank you.
I have one I couldn't help myself asking this question. So we have been investigating using deep learning model to detect vulnerability in the source code. And GC, you are in your paper, you are kind of investigating whether, or the research you are doing is attacking deep neural network, right?
Yes.
So
yes.
So if we use hypothetically, think about it. If we use a deep learning model in an IDE to detect, to help developer vulnerability, an attacker knows what that model is to detect vulnerability. Can the attacker attack that model? I mean, what do you think? What do you think about that?
So do you mean we have a model to detect the vulnerabilities in the software, and
Yes.
an attacker want to attack this model?
Yes.
Yes, I think it's very interesting, and I have seen some papers about attack and defense on the malware detection, malware classifier, because many researchers try to use the deep learning model to classify some malware, and attacking and defense such models is very interesting, and I think attacking such models is possible, and it is a subset, or it is a subcase of the general DN attack and defense.
Absolutely.
Yeah.
So then we need to design another model to defend the detector itself, the vulnerability detector itself. How far will it go? Like how much layer shall we go?
I think there is much to do, because building a perfect DNN that is that cannot be attacked or cannot be attacked is very difficult. I think it is there are much effort to do.
Right.
Thank you. Actually, I have another question for you, Zizi, if you don't mind. My question is about the precision recall, so the performance of the student's model that is obtained after slicing. I was wondering if you evaluated the performance of the student model that is obtained by doing slicing, because it seems from the picture that you were showing that the student model has less overlap compared to the teacher model. And,
Yes.
and my question is, does this cause a degradation of the performance of your models?
Sorry, maybe the internet is not.
I didn't
listen.
My question is whether so the student model has less overlap with the teacher model.
Yes.
And I was wondering if this would have caused a degradation in the performance, like precision recall of the student model. And I was wondering if you have any insight on it.
Yes, I think it is an important aspect to select the relevant slice, because in our experiment, the accuracy degradation is very important, and we don't want to improve the security of the student model, but the performance is decreased by a large margin. And our intuition is that there are some important ways that are more relevant or more important to some certain tasks, and we try to include such model neurons or model weights in the relevant slice. And maybe there are some other parameters or neurons that are important to other tasks, but these neurons are not related to our subject student task. So these neurons should be excluded. And in this way, we try to include as much the relevant neurons as possible, so that the performance can be maintained and the degradation is not much.
Okay, thank you. So looking at the chat, there is a question for the third paper for Larissa. Actually, there are two questions. The first question is whether the reviewer's performance vary depending on their programming experience.
Yeah, so we did this with the logistic regression models, and we found no difference, like if they have more experience or not. And these were self-defined by them. So we have the demographics and the survey after the experiment, and they defined their own level of expertise and experience with Java, because the code was in Java, the code task. So with Java, with code reviewing, with vulnerability security, and we found no significance there. The only significance that we found was actually about the variable name is coding, but it refers to if they report that they think about security. That's all. Yeah.
Thank you. There is also another question. So how did the vulnerability detection vary with increasing code complexity? Did you have the chance to evaluate this aspect?
No, this is like, let's say, the first the first setup of this experiment. So we started with simple vulnerabilities. We also wanted like the code not to be too complex, so it wouldn't be too real to the developers' experience and what they see every day. So we didn't want it to be that easy or that hard. So we checked with the security experts when they reviewed the code that we had created, if this was the case, and they said, yeah, it's still findable. It's not too hard, but it's also not too easy. To create the vulnerabilities and the code, we used the examples that are in the OWASP page. So they have some snippets there, and we use these snippets as the base to create the code review task. We believe that if we change the vulnerabilities, like if we change the code a little bit, or if we change the vulnerabilities, it could be that we have different results. So it would be interesting that we test these cases, for example.
Yeah, this was something I also was thinking during your presentation, because the type of, it seems that one of the findings was that the results that you obtain depend on the previous experience of the developer. Yes. So the selection of vulnerability then could affect somehow the performance. So I was wondering if you use any specific criteria to select this vulnerability, or because they were among the top 10, or I don't know. I just was wondering what was the rationale why you chose those two vulnerabilities in your study.
Yeah, so one of the reasons is that because they are part of the OWASP top 10 vulnerabilities. So when we talk about security and vulnerability, OWASP is a very spread and well-known foundation, and basically everyone knows about it. So they should, when you're talking about security, they should be aware of it. And this is a very nice source of resource, a source of material to study. And then we thought, okay, so this is a nice way of the vulnerabilities and to see if developers know at least these ones. I think that what could be done, because yeah, developers, they show, it seems that they need to be exposed to these vulnerabilities before. First, we need to raise their awareness. So they should be aware that there could be a security issue there. So they could have the instinct of, okay, this doesn't seem to be right, or at least they should look for other sources, like, okay, this code might be a bit weird, I should check for it, if they don't really know the vulnerability. And also they should be exposed to vulnerabilities, and they should be exposed to security issues. For example, the companies, they can have trainings, and they can allow them and allow them to study vulnerabilities besides just working and for the first time. I think that it's really hard to say this is a vulnerability if they never saw it. They can even have the feeling that it's wrong, but it's really hard for them to really say that this was a vulnerability. So they really need to be exposed to it. And one way that it could be done is through trainings. Another way could be, for example, to have sessions where you have a mentor, for example, you have someone that is a senior, and you do the code review together. And the junior developer, for example, they can learn more from these. And in this way, they are being exposed to someone that has more experience with security. Actually, I think that it depends on the experience. Yeah.
Thank you very much. We have also a question for the fourth paper for Sinan. Does detecting dangerous API in the call graph require code coverage test or something that covers every call flow?
No, there are two questions. First question is how to detect the dangerous API in the call graph. If I think there are, how to say, Our tool is it only performs static analysis, so it doesn't need to run some tests. It only do statically scanning the code, so it doesn't need test. But to identify the dangerous APIs, as I've seen the slides, that we might search dangerous APIs from the Andros official documentation, because it will write which API needs which permission. If it doesn't need a permission, so then it is not a dangerous API. So we can collect the dangerous API list from the official documentation. And for the second question, that yes, we should do the call graph analysis. One of the major contributions for our detector is to model the asynchronous permission management and usages. So we divide such usage to synchronous usages and asynchronous usages. As for the synchronous usages, it can build a call graph from some algorithm you can learn from textbook, like CHA algorithm or Spark algorithm. It is you can find such implementation from like we use Suit. It's a famous static analysis framework, so we can build call graph for us. And as for the asynchronous part, we should reconstruct the calling order. Like for the intercallback, we should reconstruct the calling order of asynchronous event for Android components, like on create, on resume, on click such API, we should reconstruct its calling order. So this is this part we should take some programming effort. And also we built the intercomponent communication graph. This graph can represent the calling relation between Android components. So you may imagine it's also such a calling relation. So this also takes some, we should write code to build such graph. Yes.
Okay, thank you. If you can type them on the chat, or you can switch on your microphone and ask question directly. So let's see if anyone else has other questions.
Yeah, Sauter.
Yes, please, Larissa.
Yeah, so when you're using the deep learning model, how do you deal with configurations in the files? For example, I saw that one of your code snippets was in C, and you can have these macros if devs, and the vulnerability may manifest depending on the configuration that you choose. So how does the model behave on that?
So as of now, most of the vulnerability detections in using deep learning are aimed at classifying functions. Given a functions, the model will try to classify it whether it is vulnerable or not. However, you are absolutely right that the function, the vulnerability can manifest itself across multiple functions, even across files, some macros beyond functions. So there are some techniques. For example, there are some papers, Waldy-Pekard, CCVR, which actually try to classify, take the slice out of a function, out of a code, and whatever the slice actually entails, and try to classify the slices. That can be one way to go. Another way is going forward, say right now we have dealt with functions. We can go for the files and try to classify whether this file contains some vulnerability. We don't know which part of the file may be vulnerability, but we can classify whether this file is vulnerability or not.
Okay, understood. But like if def is inside the function, and if turning, depending on the configuration that you choose for these if defs, then you can have a vulnerability or no. Do you consider this, or is the process only after like the compilation? Because this is a pre-compiler problem.
As of now, To my best knowledge, this kind of configuration is not being considered in deep learning based vulnerability detection. I mean, that again, that is to my best knowledge. So
Okay.
we have to, like, I will have to check whether some other approaches does that.
Okay, thank you.
Thank you. Does anyone have a question? Anyone from the audience? Actually, I have a quick question for Shaikat. So my question was related to, first of all, why did you focus on static analysis? And because there are other techniques to detect vulnerabilities. And according to which criteria you choose the machine learning algorithms that you selected and the tools that you tested?
So when a wide majority of the vulnerability detection techniques, deep learning based vulnerability detection techniques available, which actually treats code statically. Or a lot of these techniques do not do any kind of dynamic analysis on the code. In fact, a lot of the data sets available, there is no test cases available to test dynamic analysis, to do the dynamic analysis. So that's why we chose like these static analysis based deep learning based vulnerability detection techniques to see whether these actually work to detect real world vulnerabilities, or if these work only with, say, the data set it is trained on. And since it is a journal first paper, we wrote this paper a year back in 2020. So that time we investigated all the available techniques, tools and techniques for deep learning that uses some kind of deep learning based vulnerability detection. That includes SysVR, Vultipekar, MuSysVR. Although we did not include MuSysVR in our paper, but we did investigate that. And then there's a graph-based model called Divine. We also investigated. So that time we selected all the available techniques that use deep learning based techniques for vulnerability detection. Does that answer your question?
Yes, that answered my question. Okay, anyone else from the audience? Okay.
I have one question for Jichi. So this is not particularly related maybe to your paper, but in general, when you take a slice out of a deep learning model, whatever the model might be, is it always lossless? Can there be some information, say you take a slice, can there be a loss of information maybe?
Yeah, you mean what information is lost?
What I am asking is, when you take a slice, say when you take a slice from a source code, it's not always lossy. But when you take a slice from a DNN, it might be lossy, because DNN is kind of, all the neurons are connected to everything else. If you just take a chunk out of it, some connections are missing, and the information that is embedded in those connections are actually going missing. So in your experience, do you see any loss in the information that is learned by the DNN?
I think slicing DNN indeed, yes, lost some information, and it is so we should carefully select carefully choose what information you want to trade off, and what information you want to include in the slice. Just like in our paper, we want the relevant slice to include only the only include the information that is related to the target student task, and maybe there are some information that related to the other student tasks. For example, maybe our goal is to apply the slides to the autonomous driving task, and maybe for DN trained by ImageNet, it can also classify some other animals or people, and those information are we can lose that information, and so I think slides. I think slicing at the end is you should trade off what you want to maintain or what you can lose.
I see.
Thank
Cool,
you.
thanks.
I see Martin. I'm not sure if you would like to ask a question.
We cannot. I
We
cannot
cannot
hear
hear
you.
you.
I can hear you. Yeah.
Yes, and we can hear you now.
No.
No.
No, I still can't hear.
I still cannot hear you.
No. So I don't know. Maybe an option will be to type the questions on the chat, so at least we can read. Okay, Larissa, can your result be generalized to other interesting perspectives other than vulnerabilities?
I think this is a very interesting question. Maybe yes, maybe no, but I don't think that we should generalize it because we really only tested on the vulnerability setup. If we tested with other problems, for example, completion errors, other types of bugs, code smells, I think that we can expand the experiment to any kind of problem issue in the code. It can also be like performance issues, regressions. So we can do the experiments and test it. And I think the setup was very nice to test this kind of investigation. However, I wouldn't generalize it for other types of issues right now.
Okay, thanks.
Oh, no, I can hear you.
We can hear you now. So I just have a last question for Sinan. So a quick question. I was wondering if there were any asynchronous, if you were able to test if you could detect all the calls, asynchronous calls, or if there were any limitation of your approach in the detection of asynchronous calls and in their order. For example, there was anything you were not able to model?
Sorry, do you mean how can we detect asynchronous calls or?
Yeah, so one part of your approach is to detect, is to reason with asynchronous calls. When you have asynchronous call, this could be, their order could change, for example. And I was wondering if you did any investigation in aspects that your approach is able to model, represent, and not.
I think we have analyzed two types of asynchronous call. One is the intercallback relation. That's this such kind of asynchronous model because we want to answer so for the calling order of intercallback APIs, there is the Android lifecycle model, so their calling relation is already fixed. So we just only need to analyze whether the cost of permission management, that's permission check, and the dangerous API, if they are calling order following the Android lifecycle model, they can be safe. That is